In this lesson, we're going to introduce formulas for the derivatives of the sine and cosine functions. We'll begin by taking a look at the derivative of the sine function graphically, and then we'll turn to an analytical method to kind of confirm the results we obtain graphically about the sine function. Let's start by looking at how we can determine the derivative of the sine function by using a graphical approach. The key thing to remember here is that derivatives are functions. So if you have a function f of x, its derivative, call it f prime of x, is another function. And since f prime of x is also a function of x, we can do all the things we would normally do with a function using f prime of x. And in particular, we can draw the graph of f prime of x. This will be a big theme for us later in our course, looking at the relationship between the graph of a function and the graph of its derivative function. Right now, though, we'll keep it in mind mainly because it's going to help us figure out the derivative of the sine function. The way we'll do this is to produce the graph of the sine function, and then we'll use the shape of the graph to figure out what the derivative of the sine function probably is. After that, we'll confirm our prediction analytically by giving a little proof using the limit definition of a derivative. And we'll also take a little bit of time to examine the derivative of the cosine function. So let's begin by identifying places on the sine function's graph where the tangent lines are horizontal. So we're going to look at the graph of y equals the sine of x over the interval from 0 to 2 pi. Remember that that is one period of the sine function. So beyond there, the graph will just repeat again and again. We'll also look at the tangent lines of the graph of the sine function at where x equals pi over 2 and where x equals 3 pi over 2. Here's what we get. So we have the graph of the sine function in blue and our two tangent lines as drawn as red dashed lines here. Now notice that those two tangent lines are horizontal. Those happen to be the points on the graph where the graph sort of turns around, and that will be important for us later. So since those are horizontal lines, their slopes are 0. And since the derivative of a function gives us the slope of a tangent line of the function at a point, we can conclude that when x is equal to pi over 2 and when x is equal to 3 pi over 2, the derivative of the sine function must have the value 0. So that gives us a little bit of information about the derivative of the sine function. Let's now look at a few other tangent lines of the graph of the sine function. We'll look at the graph of the sine function over the same interval, now with the tangent lines at the points where x equals 0, pi, and 2 pi drawn in. And here's what we get. You can see the three tangent lines there drawn in red with as dashed lines again. And notice that on the left at x equals 0 and on the right at x equals 2 pi, the tangent lines look kind of the same. They have positive slopes, and in fact, they seem to have the same positive slope. At the point where x equals pi, kind of in the middle there, we have a negative slope for our tangent line. And in fact, if you examine the graph a little more closely than we're doing here, you can figure out that the slopes of those lines are 1 on the left and right and -1 in the middle. So that gives us some numerical values of the derivative of the sine function. We can make a table of these. It'll look like this. When x is equal to 0, the derivative of the sine function must be equal to 1. When x is equal to pi over 2, the derivative of the sine function will be 0. At pi, the derivative is -1. At 3 pi over 2, the derivative is 0 again. And at 2 pi, the derivative is 1 again. And those are all the things we figure out by looking at the tangent lines we just examined and their slopes. This table now gives us 5 points that we can plot that must be on the graph of the derivative of the sine function. We'll have the point 0, 1, pi over 2, 0, pi -1, 3 pi over 2, 0, and 2 pi 1. Let's look at the graph we get if we plot those 5 points. So here's the graph with just those 5 points that we found earlier. Looks like that. Now, if we fill in more of that graph, just kind of by looking at the pattern that we saw, there it is once more, in the placement of the points, here's what we'll get. And that might look familiar. That looks like the graph of the cosine function from where x equals 0 to where x equals 2 pi. And so a good conjecture that we might make, a kind of prediction, is that the derivative of the sine of x is the cosine of x. Let's turn to doing things analytically in order to see if we're correct about that. In fact, what we just guessed is correct. The derivative of the sine of x is the cosine of x. And we can confirm this by using an analytical method. We'll use the limit definition of a derivative applied to the sine of x. Now, to do this and to handle the limit that we'll obtain, we need a few resources, a trigonometric identity and a couple of limit values. The trigonometric identity that we'll use is called the sum formula for sine. And there it is. The sine of a plus b is the sine of a times the cosine of b plus the cosine of a times the sine of b. That might look familiar from your earlier study of trigonometry. We're also going to use this limit. The limit as theta approaches 0 of the sine of theta over theta is equal to 1. This is a limit we've seen earlier when we were studying limits. And we'll use one other limit, this one here, the limit as theta approaches 0 of 1 minus the cosine of theta over theta is equal to 0. Again, that trigonometric identity is probably something you've seen before, maybe in a pre-calculus course. And the limits can be confirmed graphically. So if you want to check to see that these really are true, you can draw the graph of the functions and check the limits as the input value goes to 0. Let's see how to use these to prove that the derivative of the sine function is the cosine function. Here is the limit definition that gives us the derivative of the sine of x. The limit as h approaches 0 of the sine of x plus h minus the sine of x over h. We're now going to write the sine of x plus h slightly differently. This is an application of the sum formula for sine that we just looked at. We're still subtracting the sine of x at the end of the numerator. And we can factor out and rearrange some of these terms slightly. So we'll set the cosine of x times the sine of h kind of off to the side. And then the two other terms both have a factor of the sine of x, which we will factor out. We can then rearrange things slightly more using a little bit of algebra here. So we've split our fraction that we have above into 2, where the minus sign in the numerator is. In both cases, the denominator is h, and then we're bringing out some of those constant or some of those additional factors, the cosine of x in the first term and the sine of x in the second term. Now we're going to use a little trick here that we didn't really look at when we were studying limits, but it does hold. We're going to rely on the fact that when h changes, x doesn't have to change. So the cosine of x that you see in the limit above is really sort of like a constant as far as h is concerned. Its value does not depend on h. So when we take the limit as h approaches 0, we're changing the value of h to bring it closer and closer to 0, but that does nothing to the cosine of x. It's going to stay as it is. So we can bring that out almost like a constant multiple outside of the limit. The same goes for the sine of x in the second term. That is effectively constant when h changes. The two remaining limits that you see here are the limits we mentioned earlier, whose values we could confirm graphically. The first one is equal to 1, and the second is equal to 0. And when we finish simplifying, we get the cosine of x. So this shows that the derivative of the sine of x is the cosine of x. We can do something similar for the cosine function. We can use the same graphical technique, figuring out slopes of tangent lines along the graph of the cosine function, plotting those as points on the graph of the derivative of the cosine function, and making a conjecture about what function is the derivative, we could do all that. We can also give an analytical proof very similar to the proof we just gave for the derivative of the sine function. You're welcome to try both of these. They're good practice, but we're just going to keep things short and state the derivative of the cosine function, trusting that you can work out the details if you really want to see that this is correct. The derivative of the cosine of x is negative sine of x. Fairly straightforward, except it's easy to forget that there is a negative sign there. When you take the derivative of the cosine function, a negative sign gets introduced. That doesn't happen when we take the derivative of the sine function. There's not much to say there except don't forget that this happens. It's really critical when working with the sine and cosine functions to remember that the derivative of the cosine function gets a negative sign thrown in. There is a kind of pattern that we can use here, but in order to see it, we'll need to look at the derivatives of the other trigonometric functions. And then that will give us a way to help remember that there is a negative sign in the derivative of the cosine function. We'll do that after we've introduced the derivatives of the other trigonometric functions in our next lesson.